just a quick recap of what we did last week. So mainly last week, we discussed two things: transformation between two coordinate systems. So if you have a vector, v, and you want to transfer it into a new coordinate system, so the relation would be q. This is the transformation matrix multiplied with v. So v is the original vector, and v dash is the new vector, and the q is the transformation matrix. If you want to transform a tensor, just use black. So t dash is equal to q multiplied with t multiplied with q. So this is the transformation for a tensor. This is the transformation for a vector. And you can transform these vectors back into the original system by using the transpose of the transformation matrix. So v can be obtained back if you use q transpose multiplied with v dash, and also t can be obtained by finding the transpose t and the q. Now these are, so this is the transformed, and this is the original. You start with a q or with q transpose, and you can obtain always the vector back by using the same transformation. Just you need to basically transpose it. So this is pretty much most of the time, and we spent quite some time discussing this idea of transformation last week. And then we moved into finding the eigenvalues and the eigenvectors. Let us solve this example then. Okay, so we have the tensor to be 5, 2, 0, 2, 0, and 0, 0, 3. And we want to find the eigenvalues and the eigenvectors. To find the eigenvalues, you just need to subtract lambda from all the diagonal terms, minus lambda, and this is minus lambda. And you make the determinant of this matrix equal to 0. So you need to expand to find the determinant. Usually, if you have an entire row or entire column equal to 0 except for one number, then in this case, it is easier to try and expand using this row or this column. All right, so it's better to start from this column, because if you expand according to this column, you have an equation that is easier to solve. So expand according to that. I'm going to expand according to this column. So basically, you have 0 multiplied. I don't know if you are familiar with finding the determinants. I probably just mentioned that as well. So first of all, you expand according to a certain row or a certain column, for example, this column here. And then you take the first entry to be positive, the second to be negative, the third to be positive, and you switch between positive and negative. You start from the first, you remove the entire row and column. You are left with a small matrix you need to find the determinant for. So it is 0 multiplied with the determinant of this guy, added to minus 0 multiplied with the determinant of this guy. So you have 5 minus lambda 2, 0, 0. Now this is 0 multiplied with the determinant of something. 0 is going to cancel out everything, so I'm not going to write that as well. You are left with plus 3 minus lambda multiplied with the determinant of this guy. All right, so I'm just going to write that. So you have 0 added to 0, or actually subtracted from 0, added to 3 minus lambda multiplied with the determinant of 5 minus lambda, 2, 2, and 2 minus lambda. All right, so this is basically 3 minus lambda multiplied with, I have 5 minus lambda multiplied with 2 minus lambda. And then subtract 2 multiplied with 2. This is minus 4. And this is equal to 0. Now you have an equation to solve. This is why I said you need to expand according to a row or a column which is equal to 0, because if you do that, you end up always having lambda or something minus lambda multiplied with some other equation. So basically, I mean, in principle, you need to expand this. You have a cubic equation to solve, and then you have 3 roots for the cubic equation. If you do that, solving a cubic equation is not straightforward, so you need to find some way to solve the cubic equation. Whereas if you do this, you have a linear equation multiplied with a quadratic equation. You know how to solve a linear equation, and you know how to solve a quadratic equation. This is a lot easier. So this is why I said you need to expand according to a row or a column. So you have a linear equation multiplied with a quadratic equation is equal to 0. If this is the case, it is either that this linear equation is equal to 0 or the quadratic equation is equal to 0. Obviously, both of them are equal to 0. So the roots can be found by taking this part equal to 0 or this part equal to 0. I'm going to start from this part here. It is either 3 minus lambda is equal to 0, and then in this case, we have lambda is to be equal to 3. If 3 minus lambda is equal to 0, obviously lambda is equal to 3. Alternatively, we have 5 minus lambda multiplied with 2 minus lambda minus 4 is equal to 0. And then in this case, we have, I'm going to expand that. So it is 5 multiplied with 2. This is 10 minus 5 lambda, and then minus 2 lambda plus lambda square minus 4 is equal to 0. Okay, so I'm just going to simplify this and reorganize it. I have lambda square. This is the first term. Minus 5 minus 2, this is minus 7 lambda. And then I have 10 minus 4, this is plus 6 is equal to 0. So this is a quadratic equation to solve. I have my first eigenvalue already from the linear equation. Now I need to find the second and the third using this quadratic equation. So to solve a quadratic equation, just like I said last time, you have 2 roots for the quadratic equation. It is lambda 1 over 2, or lambda 1 and 2 are equal to, and the quadratic equation, I probably just write it again here, ax plus b, or ax squared plus bx plus c is equal to 0. The roots are going to be x1 and 2 are equal to minus b plus minus the square root of b squared minus 4ac. Just shift things slightly in this direction. ac divided by 2a. So this is the solution of a quadratic equation. All right. I'll probably just move this whole thing a little bit away. Okay. Okay, so this is the solution for the quadratic equation. Now, I'm going to use that to solve this equation. So first of all, minus b is minus 7. So I have minus 7 plus minus the square root of b squared. This is minus 7 squared minus 4 multiplied with a, 1, and c, this is 6, divided by 2 multiplied with a, this is 1. So I just simplify this. Lambda 1 or 2 are equal to is 7 plus minus square root of, this is 49, 4 multiplied with 6, this is minus 24, divided by 2, and this is equal to 7 plus minus square root of 49 minus 24, this is 25, divided by 2, or it is equal to 7 plus minus 5 divided by 2. So in this case, I've got, it is either that lambda is equal to 7 minus 5 divided by 2. This is 2 divided by 2, so lambda is equal to 1. Alternatively, this is lambda 1. Alternatively, lambda 2 is going to be 7 plus 5. This is 12 divided by 2. This is 6. So it is equal to 6. So I have two values for lambda. From the quadratic equation, this is 1 and 6. So this is the values I have. And also remember, I've got already 1 that is here. So I'm just going to take it down. And put it next to the other guys here. So I'm just going to call this one lambda 3. Now these are the eigenvalues. The eigenvectors are found for each one independently. So we need to find the eigenvalues for each one of these we need to find the eigenvectors for each one of these eigenvalues. So I'm going to start with this guy, the largest one. Lambda 2 is equal to 6. So for lambda 2 is equal to 6, we have, I go back to the equation, or to the matrix here. I go back to this matrix and I replace lambda with 6. This is the value I'm considering for the eigenvalue. So I'm just going to replace this lambda with 6 and find the normal direction that would correspond to that. So I come back to this equation. I have 5 minus 6, and then 2 and 0, 2. I've got 2 minus 6 and 0, 0, 0, 3 minus 6. Multiplied with n1, n2, and n3. And then I'm just going to expand that. Is equal to 0, 0, and 0. So expanding this, 5 minus 6, this is minus 1, n1, added to 2, n2 is equal to 0. The second equation, 2, n1, and then we have 2 minus 6, this is minus 4, this is minus 4, n2. And finally, I have minus 3, n3 is also equal to 0. Now, from the third equation, you immediately get n3 is equal to 0. So you have 3, n3 is equal to 0. So it must be that n3 itself is equal to 0. If you go to the second and the first equation. Now, this is the part which probably most of you would find tricky. I'm going to probably show you that. I'm going to discuss it a few more times later on, but let us just try to solve these two equations. These are two simultaneous equations. We have n1 and n2 in them. We are going to solve for that. So to solve, you can solve by substitution if you want. So you want to cancel one term, and then you get the value of the other one. Let us try to do that. If you do this, if you multiply with 2 in order to cancel n1, you will have 2 negative n1 added to 2 positive n1 is going to cancel out, but at the same time, you have 4 n2 minus 4 n2 is equal to 0 again. So you get 0 is equal to 0, and you cannot solve nothing. Now, this is the case because basically just multiply with minus 2, you get exactly the same equation like in here. So this is a repetition. This is the same equation. And you have the same equation. You cannot get a specific, or you cannot get a deterministic, well, you can get a deterministic, but you don't get a single value for n1 and n2. See, I'm going to write down the equation here. You have minus n1 plus 2 n2 is equal to 0. This is one equation with an infinite number of solutions. So if you substitute n1 with 10, and then you get a value for n2, or if you substitute n2 with 5, you get a value for n1, and so on. So you get any value for n1, you get another value for n2, or any value for n2, you get a different value for n1. So the only restriction here is that n1 is equal to 2 n2. This is the only restriction. You pick any solution you want. This solution is always going to be that n2 is equal to half n1, or n1 is equal twice as big as n2. So the easiest thing for me in this case is just to have n2 equal to 1 if you want. n2 is equal to 1. This will give me n1 is equal to 2. So I'm just going to write the vector now. N is n1 is equal to 2, n2 is equal to 1, and then the third component is 0. So this is the eigenvector which correspond to lambda equal to 6. Now, since you can get 4 and 2, or 8 and 4, or -2 -1, or -4 -1, I mean, you name it, you have as many vectors as you want. In order to get something that is pretty much a unique, usually we normalize this vector. Normalize the vector means we divide by the square, we divide by the length. The length of a vector is the square root of the sum of the squares. Okay, so I'm just going to normalize this vector now. I'm going to find the length of n and then divide by the length of n. So the length of n, I'm going to use these two parallel lines to express that this is the length. So this is the square root of the sum of the squares. So it is 2 squared added to 1 squared added to 0 squared. And this is the square root of 4 added to 1. So this is the square root of 5. So in order to get a unique vector, just normalize, divide by the square root of 5. All right, so if you divide by the square root of 5, you get n to be 2 divided by square root of 5, 1 divided by square root of 5, and 0. And this is the eigenvector which corresponds to lambda equal to 6. Okay, so I'm just going to do the same thing for lambda equal to 1. Again, the matrix is 5, 2, 0. So I just need to subtract lambda equal to 1 from all these diagonal terms. So it is 5 minus 1, 2, 0, 2, 2 minus 1, 0, 0, 0, 3 minus 1. This is multiplied with n1, n2, and n3. And this equal to zeros. So I've got 4 n1 added to 2 n2. I've got 2 n1 added to 1 n2 is equal to 0. And finally, I've got 2 n3 is equal to 0. Now, this is immediately going to give you n3 is equal to 0. If you look into these two equations, again, 4n1, 2n2, or 2n1, 1n2 is the same equation. Just multiply this with 2 or this with half, you just get the same equation. Now, this will give you, choose any one of them you want, you will have n1 is equal to half n2. So it's half negative, sorry. So take this one to this end and divide by 4, you get to have a negative half n2. So if you substitute 1 for n2, you will get 0.5 negative. So you have minus 0.510. This is for the vector n. This is the eigenvector. This is the eigenvalue, or this is the eigenvector for the eigenvalue lambda equal to 1. Again, I'm just going to find the length and divide by the length. So the length of this is going to be n is equal to the square root of 0.5 negative squared added to 1 squared. So it is going to be 0.25 added to 1, square root of that. So this is going to be 1.25 square root of it. And I'm not going to calculate the exact number for 1.25, the square root of this. I'm just going to divide by it. So n is equal to minus 0.5 divided by the square root of 1.25, and then we have 1 square root of 1.25, and then we have 0. This is the normalized vector, and this is the eigenvector for lambda equal to 1. And then finally, we have the eigenvalue which correspond to lambda equal to 3. So we have 2, and 5, 2 minus 3, 5, and 0, 2, 2 minus 3, and 0, 0, 0, 3 minus 3. I'm just going to do this because, sorry, it is 5 and 2. I'm just going to do this last one because it's slightly tricky. There is one question that I keep perceiving. I think it is easier to show it for you once, and you would all see that. So let us again simplify this. So 5 minus 3, this is 2, and 1 added to 2 and 2. And then you have 2 and 1 minus n2. This is equal to 0. This is equal to 0. And then you have 3. So this is 3 minus 3. So this is 0 multiplied with n3 is equal to 0. Let us start from this equation, just like we did in the past. Oops. Like we have been doing so far. So I'm just going to take this equation here. So I have 0 multiplied with n3 equal to 0. What is the value of n3? So basically, n3 can be anything. So you pick any number you want. As long as you multiply it with a 0, it's going to always result into a 0. So n3 is not limited by anything. So you don't have to pick n3 to be equal to 0. You need to pick something else. So I'm going to pick, I don't know, 10, for example, or 13. Let us pick an odd number. 13, I'm going to show you why to pick 1 always, but I'm going to pick an odd number, and then we are going to see why this would be relevant. So now you have the two equations to solve. Now these two equations are now unique equations. This is the singular equation, and these guys are the unique equations. So you can now solve these two simultaneous equations, and you get values, specific values for n1 and n2. Let us take this guy away for the time being and try to solve these two equations here. So I have 2n1, 2n1, so I'll multiply with minus 1 and add both of them. I have 2n1 minus 2n1, this is 0. I have minus n2, 2n2, this is 3, added to 3, n2 is equal to 0. And if 3n2 is equal to 0, this will give me n2 is equal to 0. If n2 is equal to 0, you substitute either here or here. This will give you n1 is also equal to 0. So you have a very specific number for n1 and n2, and this is equal to 0. Now, the length of this vector is going to be the value of n3. So if you pick n3 equal to anything and then you normalize, you will get this to be back to 1. So let us assume n3 is equal to 13. Then n is going to be, in this case, 0, 0, and 13. You want to normalize, you calculate the square root of the sum of the squares. So this is going to be the square root of 0 added to 0 added to 13 squared. So it is the square root of the 13 square, and this is the 13. So you divide 13 by 13. So you would always get back into 1. So I would suggest in this sort of scenarios, you would immediately select the third component to be equal to 1, and then in this case, you don't need to normalize. So in the second part, or in the second unit in this course, we are going to discuss, we have learned the tensors, and the tensors are, we basically needed to learn them in order to understand stress tensor and the strain tensor. So we are going to discuss the strain or the stress tensor in this lecture. And once we finish discussing the stress tensor, we're going to discuss the strain tensor. Okay, so today, and then I think probably not next week as well, we are going to mainly discuss the stress tensor, and then we move into the strain tensor. Okay, so first of all, I want to stress one point. What we are going to discuss in this course is going to be Cauchy stress tensor. Is it the only stress tensor? No, it is not the only stress tensor. There is, I think, 5 or 6 different types of this, 5 or 6 stress tensors. All of them are quite popular. But for structural engineering or civil engineering, we mainly discuss Cauchy stress tensor. This is the stress tensor I think you will need for the majority of you. I think for your professional life, you wouldn't be using anything else anything other than the Cauchy stress tensor. In aerodynamic, they would probably need to use Euler-Kirchhoff stress tensor. So, for example, other than the Cauchy stress tensor, you have the Euler-Kirchhoff stress tensor. You have Euler-Kirchhoff the first order and the second order, and you have other type of stress tensor. So the main difference between Cauchy and Euler-Kirchhoff is the reference. So for the Cauchy stress tensor, this is the stress you have been familiar with. The stress sigma is equal to F divided by the area. Now, what is the A? What is the area you divide by? Is it the deformed area or the undeformed area? So this is basically the big question. And this is the major difference between, I would say, the majority of the stress tensors. It is mainly how you consider the reference frame. So for the Euler-Kirchhoff, you divide by the undeformed area. For Cauchy, you divide by the deformed area. So this is basically the big difference. Now, why this is relevant? This is relevant for structural engineering or for aerodynamic or fluid dynamic problems. So for fluid dynamic problems or for cases where you have large deformations, it is very difficult to find the deformed area. So you always go back and divide by the undeformed area is known for you. But for the Cauchy case, the deformed area and the undeformed area are very similar. There's very small deformations in there. And this is basically how the assumption of deformed area would still be valid. So we divide by the deformed area, assuming that the deformations are very small. So the deformed or the undeformed area are pretty much similar. And this is a case where both type of stress tensors are pretty much going to be equal to each other if you have the deformations to be very small. So I'm going to explain the mathematics behind this. This is Cauchy. This is the guy. He developed his tensor in the 19th century. So as I said, the majority of the continuum mechanics work goes back to the 19th century. And this is Cauchy. He developed his stress principle back in the 19th century. Now I'm going to discuss the Cauchy stress principle. I'm going to explain the math behind it, a little bit of discussion on the math behind that, and then we are going to solve an equation. So the math I'm going to discuss, or the derivations I'm going to show you, are important for you to see at least once. All right, we are going to use this stress tensor for the rest of your life, so it is important to know where this stress tensor is coming from. But if you want to think in terms of the exams, I'm not going to ask you to derive equations in the exam. So I don't want you to worry too much if you find the math behind this to be too complex. I will try to focus on the key ideas in this derivation, and then you probably try to read it yourself if you don't understand it the first time. And if you have questions, we can discuss. If you are interested in understanding the background of this stress tensor, this mathematics would be relevant. If you really care about passing the exam, probably this math would be less relevant to you. All right. So I'm going to explain the principle, or the Cauchy stress principle, which is the reason why we call this stress tensor is the Cauchy stress tensor. It is all because of the Cauchy stress principle. So the tensor is based on the Cauchy stress principle. So the principle itself would state that if you cut an object with a plane, then the stress vector inside this object on this plane is going to be only related to the normal direction. So this is basically the principle. I'm going to say it again later on, but this is what I want you to remember for now. Just cut any object with a plane. The stress vector on this plane is only dependent on the normal direction of the plane of the cut. All right, so this is the principle itself. Now, the derivation I'm going to show you is basically just going to be the math behind this idea, but the idea itself is that the plane of the cut, the normal direction of that, is the only factor that you would consider of the stress vector on this plane. This is it. And by the way, in continuum mechanics in general, and I think for the majority of this course, if you want to define a plane, if you have any plane, you define the plane using the normal direction to this plane. So a plane is defined with the normal direction. You can define always a unique plane by only defining the normal direction to this plane. All right. Okay, so I'm going to get into the math a little bit, and then we come back to the principle itself. Let us assume that you have an object. You cut this object with a plane. So this is the plane of the cut. And the normal direction to this plane is going to be n. The stress at n is going to be the force F divided by the area A. And you assume that the area A would go to 0. So basically, it's going to be infinitely small, the area A. Now, this is going to be the stress vector on this plane at point P. Now, if you do the same thing on the other half, I mean, you are dividing this into two parts. The same plane is going to apply again on the second part. And based on the equilibrium, you'd assume that the stress vector on the first part is equal to the stress vector on the other part with a negative sign. All right. See, the plane on the other half is going to be minus n, the definition of it. If this is n, then the other plane, or if you are interested in the other cut surface, the n is going to be negative in there. And we are always interested in the outward going n. Okay, so this is minus n, this is n. So t minus n is equal to negative tn. This is because of the equilibrium. All right, so this is the first point. And in general, I would say that t is a function of space and time as well. So it is not only a function of n, because at the same point, at the same x, and with the same n, you may have a different value based on the time. So stress can be changing with time, or at different time points, or at the same time point, if you fix t, and again for the same plane, if you change the location, then you will have again a different stress vector. So the stress vector is basically dependent on time, dependent on space, and dependent on the plane of the cut. The plane of the cut, this is the normal direction. Now, the Cauchy stress principle, which I mentioned, would say that the stress vector Tn is equal to the stress tensor T multiplied with the normal direction. So the stress vector is only dependent on the normal direction. This is the only thing that is going to vary, and T is basically the stress tensor at this point. Or if you want to write it in matrix form, this is the way to write it in matrix form. So in principle, this is what you need to remember, this equation here. And we are going to solve quite some equations, or we're going to solve some equations, and you'll find more examples in the tutorials that all utilize this equation. So this is basically what you need to remember. Now I'm going to show you that this is the stress tensor. Basically now what I'm going to show you is this is the stress tensor. And in order to be a stress tensor, or in order to be a tensor in general, it will need to be a linear transformation. So what we are going to prove now, we are going to prove that this is a linear transformation. All right. So now let us prove that T is basically a linear transformation. So we will go back to a very small tetrahedron. We have the coordinate system x1, x2, and x3. We have a very small tetrahedron. The length of this tetrahedron in the x2 direction is delta x2. This is delta x1, and this is delta x3. All right. On each surface of this tetrahedron, you have a stress vector. So on the first, on this surface here, so this is on the plane x1 and x2, the normal direction to this plane is x3. So I'm going to call the stress vector on this surface T E3 because it is pointing in the negative direction. I'm going to call it 2 negative E3. The same is true for this surface, and the same is true for the bottom surface. So this is minus E1, minus E2. And then on the fourth surface, this is the triangle ABC. On this surface, you have the vector, the general vector Tn, and the normal direction, the general normal direction n, which you don't know for the time being. So first of all, let us discuss the parameters of this tetrahedron. The volume of this tetrahedron is going to be 1 over 6 multiplied with delta x1, delta x2, delta x3. This is geometry. The area of A1, this is this surface here. This is A1. I'll probably just try to draw it here. I don't want to mess around the picture because it is quite small and a lot of details into it. So this is the first triangle, delta A1. The area of delta A1 is half delta x2 multiplied with delta x3. This is the area of delta A1. Now you can do the same thing for A2 and A3. So this is the area of A2, and this is the area of A3. Sorry, this is the A3. There's a mistake here. And then ABC is the area of AN. All right, I don't know for the timing, I don't know what is the area of AN. I did not calculate the area of AN. So we will leave it for the time being. Now, the vector or the stress vector on this face is equal to the area or the force that is active on this face is basically the stress vector multiplied with the area of the face. So I'm going to calculate the forces, and then I'm going to use the equilibrium equation or the Newton law, the conservation of momentum, in order to be able to write an equation that would link all these stresses together. So you calculate the force on the first face. This is the stress vector multiplied with the area, the second with the area, the third with the area, and you do the same thing for Tn. I don't know the value of Tn for the time being. I'm just going to calculate it in parametric form. All right. So I have all the forces acting on this tetrahedron. I now can use the Newton law, the conservation of momentum. Now let us take a very general case. Let us assume that this is in motion. This is a dynamic problem. So you have some acceleration. So you have body forces as well. So the body forces are the acceleration multiplied with the mass, and the mass is the density multiplied with the volume. So this is the body forces we have, and then we have a summation of all the forces that are active on this tetrahedron. So this is the first, the second, the third, and the force Tn. So all of them added together. All right. Now, the vector n, which is basically the vector on this surface here, will have these components. As I said, these are general components, n1, n2, and n3. And n1 is the component in the x1 direction, n2 is the component in the x2 direction, and n3 is the component in the x3 direction. Now, the area of A1 is basically equal to the area of delta AN, which is, as I said, this is the general surface that I don't know, multiplied with the component of N1. And this is a mathematical principle. If you want to find a projection, you multiply with the normal direction. All right, so this is math. So this equation comes from math. The projection is going to be equal to the area multiplied with the normal direction. So the delta A1 is equal to delta AN multiplied with N1. which is the component of the normal direction, and n2 multiplied with delta an is equal to a2, and the same is true for delta a3. So I'm just going to come here and replace this one with delta a1 multiplied with n3, and this one with n2, and this one with with n1, and then I'm going to take delta an as a common factor. And remember, on this end, I have the density multiplied with the volume multiplied with the acceleration. So the volume here, it is basically the an multiplied with the height of this tetrahedron multiplied with 1/3. So this is, again, this is a geometry. So I'm just going to replace that in this equation and cancel out all the terms that are dependent on delta an. I'll be left with this equation. Now, if you assume that the tetrahedron is really very small, h would go to 0. And this term here is going to vanish. And you will be left with the other terms here. So this is basically Tn and Te1 multiplied with n1, Te2 multiplied with n2, Te3 multiplied with n3. And if you just rearrange, you get this equation here. So this is the first equation. Remember, we are trying to prove that this is the stress tensor multiplied with n is basically a linear transformation for this n. All right, so this is the first equation we have. Now, let us assume that this is a nonlinear transformation, and we prove that this is not the case. We can come back and show that this is a linear transformation. If it is a nonlinear transformation, then we can write it in this way. So Te1 multiplied with E1 is equal to Te1 and E2 and E3. And then in this case, we have, if it is a nonlinear transformation, we are going to try and expand it. So you just multiply it with n. N is going to have components in E1, E2, and E3. You multiply it, and then you get these components of the stress. And you have an expression that is going to link all of them. Then in this case, you have already, you know that Tn is equal to these values there. And then you can get into this conclusion here. All right, see, you have basically these components here, because you know, you're getting these ones from here. So this one is equal to this one, you replace it with this one, and this one is equal to this one, you replace it, and you have this equation from the past. So you have Tn is equal to these guys here. Now, at the same time, you know from the beginning, right from the beginning, that Tn is the normal direction multiplied with t. So you have that written here as well. So you have both sides to be equal. And if this equation is satisfied, this will mean that this is a linear transformation. So if it is a nonlinear, this equation cannot be true. But we know this equation is true because we know that Tn is equal to these quantities there. Okay, so I probably suggest that you read it one time on your own, and then you probably see things slightly in a better way if you are interested. As I said, if you are interested in passing the exam, probably this is not very relevant to you, but if you are interested in the Cauchy stress tensor itself and understand how it actually works, probably you are interested in reading that. And then in this case, you probably try to read it one more time. And if you have any questions, I'm happy to discuss them with you. All right, so this is then T here is a linear transformation. And this linear transformation we are going to call Cauchy stress tensor, because these points I'm going to discuss now are going to be related to the application of the stress tensor. We know now T is the stress tensor, and it is Cauchy stress tensor. And everything we have learned about stress tensor, or everything we have learned about tensors, is correct for T. So we can write the components of T in a coordinate system as T1, T12, T13, and so on. We can transform it between coordinate system. We can transform from one coordinate system to another coordinate system using the Q matrix. We can find the principal values and the principal directions, and we can find invariants or different properties of the stress tensor. So we basically can find quite a few properties of the stress tensor if we wanted to. So we manipulate it in any way we want. So first of all, I'm going to probably write the stress tensor here and explain about the components slightly. So the stress tensor T, we can write it in this form. This is T11, T12, T13, T21, T22, T23, and T31, 32, and 33. And each one of these components, now this is something you have to do, or probably you have to understand in order to understand how the stress behaves. So this is I'll probably try to draw the cube here, use a different color for the cube, or probably just use the black for that, and then okay, so this is a cube. And the stress acting on this cube are going to be normal stresses. This is T11, this is T22, and this is T33. All right, so these components are normal and act in the same direction as the normal to this face. So if this is the normal to this face, then T11 or T22 or T33 are exactly parallel to the normal direction. Now this is in the coordinate system X is 1, 2, and 3. And then this is going to be E1, this is going to be E2, and this is going to be E3. And E1, I'm just going to write it down here. E1 is basically going to be 1 in the X direction and 0 in the other two directions. So it is a vector of length 1 that is pointing in the X1 direction. Similarly, E2 is going to be 0, 1, 0, and E3 is 0, 0, 1. All right, so these are the basis vector, and the normal stresses point exactly in the same direction as the basis vector. Now, beside these normal stresses, you have these shear stresses. So these are the normal values, and these are the shear values of the stress. Now, the shear values of the stress, they act parallel to the surface and perpendicular to the normal direction. So you have one in this direction and one in this direction. So this one is T21, this is T32. And the same would happen here. This is T1, 2, and this is T3, 2, and the same is also here. And these are the components 3, 2, and 3, 1. Now, each one of these components, you can think of it as having two directions or two indices or two identifications. One identification is related to the surface that is active on. So all these values here, T11, T21, and T3, sorry, this is 3, 1, are active on the plane that is perpendicular to E1. So if you multiply with E1, you will only have the values that are active on the plane of E1. So if you multiply this with 1, 1, 0, you will have T11, 0, 0. So it is T11, and then T21, 0, 0. and 3, 1. So these are the forces, or these are the components of the stress that are active on this plane here, the plane that is parallel to E1. Now, if you are interested in the direction of these forces, you need to multiply it again with any vector. So if you are interested in which one of these are actually active in the E1 direction or the E2 direction or the E3 direction, you just multiply it one more time. I'm interested in the E3 direction, for example. So I need to multiply with E3. So 0, 0, and T, 3, 1. So this is the component that is active on the face that is perpendicular to E1 and acting in the direction of 3, E3 basically. So these are basically the components, and these are the two directions that are related to each one of these components. As I said, these are normal and shear components, and they are identified by two indices. Now, so far, we don't know if these two components are equal or if this T matrix or T tensor is symmetric. So we still don't know. We have proved that this is a linear transformation. We now need to show that this linear transformation is symmetric. It doesn't have to, but it is actually in the Cauchy stress tensor, it is symmetric. So to prove it is symmetric, we come back to this cube here, and we are going to look into one face. So let us look into this face here. We are looking into the face of x1, x2. So this is this face here, and these are the forces or the stresses that are active in this direction. So first of all, the dimension of the box in this direction is going to, or the dimension of the cube in this direction is going to be delta x1 for this direction, for the direction of x1, and delta x2, the length in this direction of x2. Now, on the faces of this stress tensor, also on the faces of this cube, we have the stresses. So on the directions that is normal, we have T22 and T22 and T11 and 11. On the direction parallel to the surface, we have T12 and T21. All right, 1, 2, and 2, 1. So for the time being, we don't know if these forces are going to be exactly the same or if they are slightly different. So we assume that these forces are going to be slightly different. So the stress on this face is slightly smaller than the stress on this face. So we have a high order term. This is delta T22. This high order term is the difference between the stress on this face and on this face. The same is true for all the normal directions, and the same is true for all the shear directions as well. So we have delta T21 and delta T12. Now let us take the bending, or let us take the equilibrium and check that the moments around the center of this square, now we're talking in 2 dimensions, we have a square. So let us take the bending moment, or so let us take the moments around the center of this square. So at the center of this square, the forces here are passing through the center, so they have 0 bending moment, but the shear forces will have some value. So it is, first of all, the force multiplied with the area, multiplied with the arm of the force. So let us take this one here to start with. So first of all, we have the stress. So we need to multiply it with the area to get a force. So the area is going to be the depth. This is delta x3 multiplied with this length. So this is delta x2. So this is the area. Now, this force to this center, this is the arm of this force. It is delta x1 divided by 2. And this is the bending moment resulting from this force here. We can do the same thing for all the 3 or the remaining 3 forces. We have this equation there. So the sum of these is going to be equal to 0. Now we can expand them. Just expand everything, and this is what you get after you simplify. I'll probably just show you this. So you have this term here multiplied with T21 and the same term is multiplied with t21. So this is 2t21, and then you have 1, 2, this multiply with it, and this multiply with it. So you have 2t21 minus 2t12. This is what you have there. Now, what happened to the higher order terms? What happened to these guys here? This one and this one. Now, we assume that this is very small, and because this is very small and this is multiplied even with a smaller number, because this is multiplication of many small numbers, so this is going to be insignificant and we cannot drop it out. So this is what we assume. And this is important because I'm going to talk in a minute about the consequences of that. But for the time being, we are going to drop this because it is too small. So if we drop that, we are going to be left with this expression. If you divide by this expression, you have t21 is equal to t12. If you have that, you know that then the matrix itself is symmetric. So if this one is equal to this one, then the matrix is symmetric. You can prove that in the same way, that this guy is equal to this guy, and this one is equal to this one. So if you show that, you know that this matrix is symmetric, and we know it is symmetric. I mean, you know that the stress tensor is always going to be symmetric. Now, it is symmetric. I'll come back to this point. It is symmetric because you are ignoring these high order terms. If you don't ignore them, the matrix is never going to be symmetric. And it is possible to ignore because these high order terms are basically being ignored. We are not taking them into consideration. If you have large deformation, it is not going to be possible to make this sort of assumption. Or if the variation of the stress is too high, then this assumption again is not going to be valid. So there will be cases where this is not negligible, and then in this case, you cannot make the assumption that the stress tensor is symmetric. But for the majority of the cases you will be dealing with in structural engineering or in civil engineering, you will be dealing with situations where this assumption is going to be valid and the stress tensor for you is going to be symmetric. All right, but I want you to remember that it is symmetric because we are making some assumptions in there.